Good morning and welcome to the ALCF Developer Session for December 2019. My name is Yasaman Qadar and I'm a member of ALCF Performance Engineering team organizing these training activities. These webinar series are created to foster discussion between the software and hardware developers and the early users of that technology. Today's topic is an overview of Aurora, the 2021 Exascale system at ALCF. And we are pleased to have with us Colleen, Bertoni, and Sudheer Chunduri. Colleen Bertoni is an assistant computational scientist in the performance engineering group at the Argonne Leadership Computing Facility. Her research interests include programming models for high-performance computing and electronic structure theory. Sudheer Chunduri is also an assistant computational computer scientist in the Leadership Computing Facility at Performance Engineering team at Argonne. His research focused on scalable tools for measuring and analyzing HPC interconnects performance. During the talk, if you have any questions, please type it in the chat room and I will ask those questions. We will have basically two segments of the talk that Sudheer and Colleen will talk about. Sudheer and Colleen, please take it away.
Thank you, Asi. Good morning, everyone. Welcome to the session. We are very excited to talk about the Aurora, Argonne's upcoming Exascale system. So Colleen and myself share the session today. I'm going to talk first about the hardware, and then Colleen will take from me and talk about the software. So Aurora is an Intel Cray machine arriving at Argonne in 2021. It has a sustained performance greater than 1 exaflops. The building blocks for this system and the hardware level are Intel Xeon processors and Intel Xe GPUs. The Xe GPUs are the GPUs that are announced recently by Intel. The total memory on the system is going to be greater than 10 petabytes of memory. And the networking architecture is based on Cray's latest Slingshot network. And these cabinets are going to be housed in SASTA platform that's also coming from Cray. The I/O has two layers of I/O. One is the traditional Lustre file system and the distributed asynchronous object store I/O that's called DAOS. That's a novel thing that is based on the non-volatile memory components. It has a greater than 230 petabytes of storage capacity and 25 terabytes per second of bandwidth. On the software level, the software architecture is under the Intel One API umbrella, traditional Intel compilers, C, C++, Fortran compilers. And the programming models, the DP++, OpenMP, and OpenCL. The libraries, all under the One API umbrella, One MKL, One DNN, and One DAL for data analytics library. And the vTune and Advisor, the Python, all under the Intel One API umbrella. So I'm going to talk on the hardware. First, I'll discuss about the node level hardware, then the network hardware, and then the I/O. The node level hardware, the primary compute workforce at the node level is the Intel GPU. Intel is not new into the GPU business. It has been, if you look at the roadmap of Intel GPUs, there have been GPUs primarily in the integrated market for the graphics. So it has several generations. The current generation is Gen 11, and the next generation is called Xe GPU. It has various flavors of GPUs targeting for the client segment as well as for the data center optimized versions. What we're going to have on Aurora is a Xe data center optimized GPU. So primarily, it's a compute, whereas the client's market is more towards the um, graphics kind of operations, whereas the DC data center optimized is more for the double precision optimized. The Xe GPU has two flavors, both in the integrated as well as the discrete GPU. But for the till Gen 11, all the graphics GPUs come in the form of an integrated GPU. So the Intel GPUs, as I said, these are not something new. These have been used widely in the laptops, desktops, and servers. For example, MacBook Pro has, the one that I use, has an Intel GPU. And the recent and upcoming integrated generations are Gen 9 is used in the Skylake-based nodes, and Gen 11 GPU is used in the recently announced, recently marketed like Ice Lake based nodes. To give you a rough estimate on the kind of compute performance, the Gen 9 GPU has a compute throughput of between 100 and 300 gigaflops. It's low because primarily the focus is into the low-powered segment for the graphics processing. But if you look at the chip area as such on a Skylake core, the primary, it's almost 30 to 35% of the die area is occupied by the GPU compute. So here the GPU in the graphics, compute, and media segments are there. But as you can imagine, if it is focused on the compute, the compute portions will be given more prominence in the chip area. So the Xe GPU, it's called the Gen 12 GPU series, and it comes in two flavors, integrated and discrete GPU. And what's going to be there in Aurora will be a discrete GPU version. So if you look at the Gen 9, the building blocks, just to give you a rough idea on how the internal architecture, the microarchitecture of the GPU looks. So the basic building block is called an execution unit, EU. It has, the Gen 9 has 7 threads, and it has 2 SIMD floating point units and 1 send and branch unit. Send is primarily used for all the memory operations, and the branch is for the branch unit operations. So 8 of these EUs, along with the thread dispatch unit, data port unit, and the ray tracing unit, and also the memory, the L1, L2, form a subslice. And couple of 3 subslices are form a slice, and these all these 3 subslices in a slice share a shared local memory and also an L3 data cache. So the subslice has L1 and L2, and the slice has an L3 data cache. So as you can see, the point that I want to make here is the architecture is familiar to what is traditionally seen in CPUs or GPU architectures that are existing today. And multiple of those slices form one GPU. For example, in a Gen 9, some versions of Gen 9 has 2 slices form one GPU. Just to give you an idea of how the GPU characteristics of a specific GPU that's called Iris GT4 that's coming in the Gen 9 series, it has a clock frequency of 1.15 gigahertz. That's low, but we should be cognizant of the focus market is the graphics. And the 3 slices form the GPU, and total execution units. Each slice has, as I said in the previous slide, 24 EUs, so total 72 EUs. And each of the EU has 7 threads, so total 504 threads. And the SIMD is width of 32-bit. So as you can calculate on the not going to go in detail about the all the characteristics here, but you get a rough idea of how the memory components, the loss level cache size looks. So overall, the double precision floating point throughput of around 331 gigaflops, and it has fmad kind of multiply and add. The floating point unit is capable of that feature, like multiply and add can be done in a single cycle. So if you look at the node architecture, the compute node, it has this 2 Xeon processors that's called the Sapphire Rapids processors, and there are 6 Xe GPUs that are connected in an all-to-all fashion, and the memory architecture across the CPU and GPU is unified, and each CPU has 4 network endpoints connecting to the slingshot network. So total, at the node level, it has 2 Xeon processors, 6 GPUs with all-to-all connection, and 8 slingshot fabric endpoints. Now going to the network interconnect, the network is the Cray slingshot based network, and the topology that will be used is a 3-hop dragonfly topology. If you're familiar with the Cray XC Aries topology, it's called 5-hop dragonfly, but this one is a 3-hop dragonfly. And so if you look at a group, within a group, there are switches that connect to the nodes, and all those switches have all-to-all connections. That a set of 512 nodes form one group, and all these groups connected in an all-to-all fashion with optical cables. So the idea is, from the cost point of view, the global links are optical, but the local links are electrical links. The switch that is used is Rosetta, that is publicly announced by Steve Scott, Cray's CTO, recently at Hot Interconnects, and it has like 64 ports with each port capable of 200 GB per second in each direction, and total bandwidth around 25.6 terabytes per switch. And the switch features, if you look at the switch features, it has this traffic classes, so you can differentiate the traffic and treat different traffics. You can associate priorities to the traffic, and that's primarily intended for providing isolation between applications via traffic shaping and bandwidth sharing. And the other feature is the aggressive adaptive routing. If you're familiar with the Cray XC Aries, it also has adaptive routing, and whereas there it is 5-hop, with the 3-hop, the congestion information will be more closer to recognize the congestion and take necessary action to mitigate the congestion much sooner than a 5-hop topology. And a multi-level congestion management. So to minimize the impact of congested application on others, they have at the hardware level features to detect the congestion and take mitigating actions sooner. That ensures very low average, not only the very low average latency, but also the tail latency to be very low. And the switch has the current generation switch architectures, it has high performance multicast and reduction features. Let's look closely at the traffic classes. So the traffic classes are highly tunable. The primary thing is at the network protocol level, the traffic differentiation could be done. That's the first step. Once the differentiation is done, different traffics could be given different priorities, different routing biases could be used, and also the minimum bandwidth guarantees and maximum bandwidth constraints could be assigned to the traffic, different traffics. And this cartoon here shows how different traffic type 1, 2, 3 colors, blue, red, without the quality of service. The red, which is probably an adversarial traffic pattern, could impact the more benign traffic patterns like blue or green. Whereas when there is a quality of service, then the proportionate bandwidth is given, and that constraint, the red will not affect the other traffic patterns. So it supports multiple overlaid virtual networks essentially. So high priority traffic could be defined, and low latency control and scavenger wherever there is IO kind of traffic patterns could be given low priority compared to compute traffic. And within a job also multiple traffic classes could be used. So if you could imagine like MPA collectives could be using a different traffic pattern versus point-to-point operations, or different collectives could be using different traffic patterns. And so essentially the idea is provides performance isolation for different types of traffic, and so that the small size reductions can avoid getting behind like many to one kind of patterns which are known to be adversarial. It could also be used for mitigating interference between compute and I/O. The congestion management, as I said, this is a novel thing that's going to be available in the Slingshot. I'm going to show some results as well, some initial results. So the hardware automatically tracks all the outstanding packets and knows where exactly the congestion is happening, and it's able to push back the sources, the injecting points that are causing the congestion, just the right amount, how much it is based on the intensity that congestion is generated, so that it frees up buffer space for other traffic, and more benign traffic will not be affected by the adversarial traffic patterns. So it avoids head-of-line blocking across the entire fabric. And it's useful for the dynamic HPC kind of traffic patterns that are fast and stable across a wide variety of traffic patterns. It also enables the quality of service. It enables the traffic differentiation and bandwidth sharing. But within a traffic class, if multiple applications could be within a same quality of service class, so this congestion management helps there to avoid interference among those applications that are in the same traffic class. So it enables, by this hardware management at the hardware level, it enables low, mean, and the tail latency. Essentially, the tail is very critical, because if the traditional applications which have this bulk synchronous kind of applications that use global synchronizations, the stragglers are the ones which determine the performance. So the tail effects are quite significant. So to characterize how the congestion management is operating, we use the benchmark, the newly designed benchmark called GPCNet. It stands for Global Performance and Congestion Network Test. And the idea of this benchmark is not like a traditional ping pong kind of benchmark measures network performance in an isolated environment, whereas if you're coming from office to home, the latency to commute, but actually what is required essentially is in the presence of traffic, in the presence of network load, how to measure the congestion is the idea of this benchmark. So it has some set of congestors and probes, and the congestors provide the background noise, and the idea is to measure how probes get affected by the different intensities of the congestors. So we look at in this benchmark, we look at both the mean and the tail latency, and so essentially this benchmark, we use it to see how the congestion management on the networks is operating. So for this, we ran this benchmark on several systems. So Crystal, Theta, and Edison are the node sizes are given, and the global, the tapering, I mean, how the global links, 1:2 tapering, or it's fully provisioned network. The tapering is given, and to be consistent, all the networks, we use the same number of endpoints, number of processes per network port. So different networks of different sizes, but also see that Crystal, Theta, and Edison are Aries, and Summit, Sierra, and Osprey are EDR InfiniBand. And Malbec is a 485 node slingshot based machine that's housed at Cray. That's also used for in this benchmark. So the benchmark reports the mean latency and also the tail latency. The congestion impact is calculated as the latency in the congested environment versus the latency in an isolated case. So if you look at the Aries networks, the congestion impact is in the order of like 1,000. That's quite high, and also the congestion impact is increasing with the system scale. And when you go with the InfiniBand systems, the InfiniBand performs better at congestion handling than Aries, but overall the impact worsens with the scale and with the tapering. So, for example, Summit and Sierra are similar systems, but Sierra has more tapering. So that's why you could see more congestion impact on Sierra. Whereas with Malbec, so essentially the congestion impact is not there. So the red line here shows the congestion impact. So Slingshot does quite well in mitigating the congestion. So the congestion management is, it's more to be seen at the large scale how it operates, but the initial results are very encouraging. Then that's the network part. So if you look at the MPI on Aurora, so it has two MPI stacks. One is coming from the Intel, that is based on the MPICH, open source MPICH at Argonne, and the Cray MPI. And these are MPI 3.0 compliant, and the MPI library is optimized for MPI thread multiple and thread safe optimizations, so that applications could initiate MPI operations from multiple individual threads. And the asynchronous progress in all types of non-blocking communications, like non-blocking sends, non-blocking collectives, and one-sided operations. And the hardware optimized collectives, both at the switch level and the NIC level, there are some optimizations to improve the collective performance by offloading to the hardware. On the topology optimized collective implementations, and for performance tools, MPI tools interface is also will be provided. The software stack looks MPICH, as I said, it's based on the CH4. This is then the libfabric provider, then the Slingshot provider interfaces with the hardware. Then moving on to the I/O. Okay, so the Aurora I/O subsystem has a two-tiered approach to storage. One is the traditional Lustre parallel file system, and as I said initially, it also has this novel Deos that's primarily built based on the NVM storage, non-volatile memory storage. So the compute nodes connect to both the Deos and the gateway nodes that in turn connect to the Lustre file system or the Slingshot fabric. And there is a seamless data movement between Deos and the Lustre. The Deos is the distributed asynchronous object store. It provides the main storage system for Aurora. It has like 230 petabytes of storage capacity and greater than 25 terabytes of bandwidth. It's a new storage paradigm based on NVM, using the NVM as a storage component, and enables new data-centric workflows. But it provides the usual POSIX wrapper for related relaxed POSIX semantics. The Lustre is the traditional parallel file system, provides the global namespace for the center and compatibility with the legacy systems that are there at Argonne. And storage, so Lustre primarily you could think of for the data bulk data will reside in the DAOs, and the source code, the binaries and libraries reside in the Lustre as a cold storage. Okay, if you look at the I/O from a user perspective, if a user sees this as the traditional Lustre file system, but the DAOs components are you could think of as hyperlinks to the DAOs partition, where here the HDFI container, POSIX containers, and the MPIO containers are linked to the DAOs. So the data resides in a single place, either Lustre or in the DAOs, the explicit data moment. There's no auto migration that could be quite costly. So users keep the source and binaries in the Lustre, and the bulk data resides in the DAOs, because the bulk data is the one that will be used more frequently. So the DAOs, since it provides much faster access from the bandwidth point of view, it's so the bulk data will reside in the DAOs, and the source code, etc., reside in the Lustre. So that's the end of my part. I'm happy to take any questions at this point on the hardware part.
Thank you, Sudheer. So we have a question. Are there MPI optimization for communication buffers stored on the GPUs?
Yeah. Yes. So the MPA teams are working on when the buffers are in the GPU, on the Xe GPU, how to optimize the MPA operations. That work is going on. Yeah, I think, what does DAO stand for? I think I expanded that.
So before we move on to the next step, is there any other questions related to what Sudheer covered? There is another one about coherence.
What about coherence?
I think you are talking about the GPUs and CPUs. That will be maintained. The coherency between the CPU memory and the GPU memory is maintained.
Topology is rack level.
I'm not sure I followed the question. The Dragonfly topology. So the topology at the total system level is a Dragonfly topology. I mean, so the way to think about it is, if you're familiar with Aries topology, only thing that changes is within a group, the topology changes. Whereas in an Aries, it's a 2D butterfly kind of interconnection where rows and columns. Whereas here, all the switches have all-to-all connection. But across the groups, it has an all-to-all connection similar to Aries.
Another question is, how many CPUs and GPUs are there?
So there are, per node, there are 2 CPUs and 6 GPUs. I think that same question I answered. If you are talking about the performance for all reduce for GPUs and CPUs, those details we will reveal at a later point.
And then I guess another question is, what is the speed of links between GPU and across 2 CPU sockets?
So those are under NDA, so unfortunately we can't share those now, but at an appropriate time, we'll be happy to share. Okay, so I'll turn it over to Colleen. Thank you.
Okay, thanks. Yeah, thanks, Sudheer. Thanks for the questions. So I'll talk about software and the software stack on Aurora.
Before you go on, Colin, sorry, there is one more question. Is the global links also a secret?
The global links also a secret?
What do you mean?
I guess the question is not clear.
Yeah. a lot of the specific numbers for speeds are will be revealed later.
Yeah.
If this is a question about that.
Okay, Colin, let's continue with your segment. Thank you.
Okay, yeah, thank you. So first I wanted to talk about just motivation and high-level overview of the pre-exascale and exascale landscape to sort of motivate the rest of the programming model talk and software stack talk. So I think a lot of people on this call are familiar with this, but I'll just go through it to sort of get everyone on the same page. So this is just a list of sort of the exascale and pre-exascale systems we have now. The Summit and Sierra were delivered in 2018. They're on the floor now. They're both heterogeneous systems where IBM is a CPU vendor and NVIDIA is the accelerator vendor. And then in 2020, NERSC gets Perlmutter, which is a AMD CPU and an NVIDIA accelerator. And then in 2021, Argonne will get Aurora, which Sudheer just talked about. It's an Intel CPU and an Intel accelerator. And then shortly after that, Oak Ridge will get Frontier, which is an AMD CPU and an AMD accelerator. And then after that, El Capitan, which has a AMD CPU, and I think the accelerator is unknown right now. But I wanted to go through this just to sort of show the landscape and what people are facing if they want to run on multiple systems. So the first thing is all these systems are heterogeneous systems. They're all CPU plus accelerators. And this is important because most of the floating point operations and bandwidth will be on the accelerator, so you really need your code to be able to run on the accelerator. And the other thing to note is that there's varying vendors. So at least right now on the floor, they're only IBM plus NVIDIA systems, but shortly starting in 2020, we get AMD and then Intel and then other AMD systems. So there are a variety of vendors that people wanting to write software will have to deal with in some fashion.
Colin, I'm sorry to interrupt you, but the audience would like you to speak closer to the microphone.
Oh, sorry. Okay, sorry. Is this more clear?
Yes, thank you.
Okay. Yeah, okay. So sort of the next kind of motivation slide is before we get into details, I wanted to sort of give a high-level overview of the application space that we're focusing on at Aurora. So we call this the 3 pillars. There's simulation, data, and learning. Simulation is sort of the standard HPC science applications that simulate physical phenomena that we think about. These depend on HPC languages like C, C++, Fortran. They often use directive-based parallelism, parallel runtimes, and solver libraries. But there's also the data pillar, which is usually large-scale analysis on large data sets. This encompasses things like productivity languages like Python, also statistical libraries and databases. Then there's the learning pillar, which is training and inference using machine learning techniques. So it encompasses, again, productivity languages like Python, but also deep learning frameworks, statistical libraries, things like that. So the point here is that Aurora, we're not just focusing on simulation applications, but also data and learning. And so as application developers, you maybe fall into one or two of these columns, but there's also a lot of the software that's shared between them, like compilers, math libraries, I/O. And so this is sort of informing the sort of software stack that we have. And we want to support it for different types of applications, not just sort of standard HPC simulation applications. Okay, so next I'll talk about programming models. And this is really important because, like I talked about before, if you want your code to run across different systems, you maybe have to think about what programming model to choose so that you can run your code on all systems, or maybe if you want to rewrite your code for each system, this is fine as well. But this is something you should, or we hope people are considering. Okay, so first, just like an overview of what kinds of programming models people are currently using for pre-exascale and exascale systems. This is just a list here of some of them. So CUDA, this is a proprietary model that runs on NVIDIA GPUs. OpenCL, this is an open standard from the Kronos group. It's sort of low level. There's HIP, this is also an open standard that's driven by AMD. Then there are directive-based models like OpenACC and OpenMP. These are also open standards. Data Parallel C++ and SYCL. I'll talk a bit more about this later. SYCL is an open standard from the Kronos group, the same people as OpenCL. It's sort of a C++ OpenCL. And Cocos and Raja, which are ECP-supported programming models and portability frameworks. So the thing to note is that not all systems will support all the models. Some of the models are proprietary. So when you write your code, it's important to think about this. Of course, there are some ways you maybe can get around this. So if you are lucky enough that your code, you can pull everything into libraries, and then your code will be portable because, for example, if you have a lot of MKL or DGEM calls, every vendor will have an optimized math library, and you'll be portable because everything you have is in a library. But real-life applications aren't always sitting in libraries. So at some point, when writing an application, it will be useful to look at this landscape of programming models and maybe pick one or two or some of them, or have some other way of handling this. So what is supported on Aurora? So OpenCL, OpenMP, Data Parallel C++ SYCL, Cocos, and Raja. So CUDA is a proprietary programming model for NVIDIA hardware, so that's not supported. And then for OpenACC, we think that most of what is in OpenACC can be supported with the new features in OpenMP 5.0. I'll talk a little bit about this later as we go through and get into more detail. Okay, so given that set of sort of program models that people tend to use and program models that are available on Aurora, what would we suggest people do if they want to start preparing for Aurora? So this is sort of a suggested mapping, and of course you can do whatever you want, but this is what we're suggesting right now. So if you have a pragma-based or objective-based program model like OpenMP or OpenACC, those sort of directly map to running on OpenMP. If you have a CUDA code, there are a couple of things you can do. Of course, you can map it however you want, but two suggested options are OpenCL, where if your code is C-based, OpenCL is based on C, so it sort of naturally goes to OpenCL. Or if you have a very C++-based code, Data Parallel C++ or SYCL, or maybe it would be for you. They both express similar levels of parallelism and have some similar abstractions, so both seem like they would work okay. And then if you have OpenCL, Cocos, or Raja code, right now those will run on Aurora without any changes. Okay. So next I wanted to go through sort of in a little more detail about OpenMP, Data Parallel C++, and OpenCL. And I'll start with OpenMP. So OpenMP is a pragma-based or directive-based programming model. It's available for C, C++, and Fortran, and this is really important because not all of the programming models have native or a lot of Fortran support, but OpenMP does, so OpenMP is a really good choice if you are a Fortran developer. OpenMP has been around for a very long time. It's a portable model that other systems have said they will support as well. So Aurora, Frontier, Perlmutter, a lot of the other systems on that previous list will also support OpenMP. It's sort of the de facto standard for certain things in HPC, so it should have a lot of support and be very portable. Intel will provide an optimized version of OpenMP for Intel GPUs and for Aurora. And I wanted to come back to the OpenACC thing a little bit. So OpenACC codes could be converted into OpenMP for Aurora. We will have staff to assist with the conversion. We'll probably have training and also best practices for how to do this. There also are some automated translation tools like CLAC, which take OpenACC code and turn it into OpenMP. Source-to-source translations are always difficult to get well, so manual intervention usually has to happen. But again, we will have staff to help with this. And I mean, we are excited about Aurora and we want people to be able to run on it. So if you do have an OpenACC code that you are worried about running on Aurora or you want it to run on Aurora, please email me or Sudheer and we can try to assist with the conversion or figure out how to help with that. Okay. So here's just I'll go through a quick code example. And I'll start just by looking at sort of the top of the screen. Probably everyone on the call knows this, but just to make sure everyone's on the same page, just the sort of mental model you can have when thinking about this sort of programming is a host, which is a CPU, and a device, which is a GPU. And basically you want to run code on the device, so you want to start running on the host and transfer execution control to the device. And then you also want to be able to transfer data so that the code that is on the device can compute on it. So these are sort of the two important things to think about when doing this kind of programming. So this sort of shows a simple example here, where in red, the pragma OMP target is the code, the directive-based code in OpenMP that says transfer execution control to the device. And then the map clauses in green transfer data from host to device. So map2 takes data from the host and moves it to the device, and map from takes data from the device and moves it to the host. So again, all you need is like a couple of pragma to set this up. And if you're familiar with CPU multi-core based OpenMP programming, you maybe would have had a pragma OMP parallel 4 there before. So this is sort of changing it to target teams, distribute parallel 4. But what I want to say is, if you've already done the work to figure out where your parallelism is in your code and you've already added pragma parallel OMP parallel 4 to it, then you can sort of take that as your baseline and start trying to add in pragma OMP target teams, and you can sort of already get started with switching your code from CPU parallelism to GPU parallelism. So if you've already gone through that work, you already have sort of a head start for running on GPUs as well. So that work has not been wasted, basically. Okay, so a little more. So OpenMP, I showed just a couple of directives, but it is a really rich specification document with a lot of different pragma that can help you do different, more specialized things on GPUs. So in particular, I talked, sort of the three main categories are shown here, and I talked about before ways of handling execution control, so pragma OMP target, and some other ones, ways of controlling data transfer, like the map clause, but there are also other pragma for unstructured or moving data in unstructured blocks, and different ways of mapping parallelism to GPUs, so trying to match the hierarchical parallelism that are on GPUs with things like teams distribute parallel 4. So the other thing I want to mention is that if you can write your code right now and get ready for Aurora without having access to a GPU, you can write pragma OMP target teams and offload instead to a GPU, just offload to the host. And so you can start working right now without having access to a GPU. There are different environment variables like OMP target offload. If you set that to disabled, then that will offload and run on the host instead of the device. So you can do this sort of step-by-step porting process where you start with your code on the CPU. You can start adding in these pragma for GPU programming or accelerators, and still offload on the host and debug and get your code ready that way, and then run on a GPU later. Okay. So next, I want to switch to talking about data parallel C++ and SYCL. So, and the relation between the two. So first, I'm going to start talking about SYCL. This is an open specification from the Kronos group. These are the same people who define the OpenCL specification. The main thing about SYCL is it's sort of a C++ version of OpenCL, so it's based on, right now, C++ 11. And it builds on a lot of the OpenCL concepts, like the same sort of thing like work items and a lot of the similar concepts, but it is single source. So in OpenCL, often you have one source file that has host code in it or host source in it, and another source file that has device in it. And here you can have one source file that has host and device in the same source file, and I will show an example of this in a bit. So it is very C++ oriented. So if you like C++, this may seem like a natural fit for you. And like shown in that image to the side, the SYCL 1.2.1 spec, which is the current spec, it also includes all of C++ 11. So this is an open standard, so a lot of people have implementations of SYCL right now. Compute CPP is probably one of the biggest ones. They have implementations that will run on many devices, including Intel GPUs. Intel has a version of SYCL. It's available on GitHub. There's also TriSYCL and HipSYCL. HipSYCL has the SYCL runtime on top of HIP. And so today you can run this on many devices, and there are many implementations, like many CPUs, many NVIDIA, AMD, and Intel GPUs. So this is not just Intel, this is a lot of other people who are interested in using SYCL. So how does this fit in with data parallel C++? So data parallel C++ is part of the one API specification, and I'll talk a little bit more about that later. This is basically just SYCL plus a couple of extensions that are useful for people in HPC. So I think the totality of the extensions are shown in that table. And the link at the bottom, you can find out more information. But I just wanted to mention specifically things like an extension is to have unified shared memory, so you can use a pointer on the device, the same pointer on device and host. Reduction, so you don't have to write your own reduction. You can use a reduction that's already there, kind of like OpenMP provides a reduction. And so data parallel C++ is mostly just based on this open standard SYCL. And so this will be optimized for Aurora, but it's not just for Aurora and Intel GPUs. A lot of other people can use it on other systems as well. Okay, so now I wanted to go through, similar to before, just sort of a quick example so you get a sense of what code written with SYCL will look like. So again, the mental model you can have is like a host and a device where the host is CPU and device is GPU, and you want to transfer data and execution control. So the first thing here is to decide what device you want to run on. So this is with a selector. There are CPU selectors, GPU selectors, and accelerator selectors, so you can select FPGA or something like that. There's also the default selector, which on the system that I run on now, this always ends up being the GPU, but if you want to be more specific, you can use a CPU or GPU selector. So once you've defined that, then you set up a queue. The queue takes in a selector, and the queue is what you will send work to, like kernels to, and they will run on the device that you selected with the selector. Then after you've done that, you set up your buffer. This is the data that you'll be using on the device. And then once you have the buffer and the queue, then you want to submit work to the queue. And so this is, you can see the C++ part of it. The submit function takes in a function object. And so to do this, we create a lambda where we capture by reference, shown there. And then once you're inside of that, you create an accessor for the buffer. And the difference between the buffer and the accessor is that the accessor says how the data is accessed. And the nice thing about this is it gives the SYCL runtime the ability to optimize data transfer for you instead of you necessarily explicitly moving data back and forth. You can explicitly move data back and forth, but this will do it for you. So you say, maybe I only want to read this or I only want to write this, and then the SYCL runtime can optimize where the data is at one time, like whether it's copied back and forth to the device or if it stays on the device. And then up until this point, we've only been running on the host, but next we finally define the kernel. And this is done with the parallel 4, so this is sort of similar to OpenMP where you have a parallel 4 or OpenCL. And so here we say we want to run 1024 work items, and we get back at the index with IDX of all the work items. And inside the kernel, all we do, this is just a simple example, is set that buffer that we already defined, the index equal to the index of the work item. And then that's the kernel that will run on the device. And then this is C++, so scoping is important. In particular, when the queue goes out of scope, then the queue's destructor is called, and it's a sort of synchronization point, because all of the kernel, if you put a bunch of kernels in the queue, all of them have to finish before you go out of scope. So that's, you know, once you go out of scope of the queue, that all of the work you've put in the kernel has already finished. There are also ways to explicitly say wait for something to finish, but this is one way to do it. And there have been previous SYCL talks, and there's a lot of training material you can find. So if you're interested in this, please look into it. Okay, just one slide, a little bit about OpenCL. OpenCL has been around for a long time. It's also an open standard from the Kronos group, which is the same as SYCL. A lot of people have used it before for CPU, GPU, FPGAs. There are many implementations from many different vendors, AMD, Intel, NVIDIA. The Intel implementation, which will run on Intel GPUs today, is open source, and you can find it on GitHub. It's a SIMT programming model, single instruction, multiple threads. This is similar to CUDA. So inside, like OpenMP has pragmas you add around loops. This is just, you define the kernel, and a bunch of threads or work items will run the same kernel. And it's based on C, not C++. And there are examples you can find at the link shown there. So I wanted to briefly mention one API because this was made public at SC19 this year. And I wanted to sort of be clear about what the relationship between what's on Aurora and what's in one API and all that is. So first, one API is an industry specification from Intel. This means it's a specification document. You can go look at the document at the link there. What I mean by industry specification is it defines a language and libraries that target programming across diverse architectures. So for example, the language that it defines is data parallel C++ that I mentioned before, and it has various APIs like MKL and math libraries like that. And so what this means is that this is specification that any vendor can take and implement themselves and run across different platforms. So like how OpenMP or MPI is a specification, and then a lot of different vendors have different implementations of it. And then on that note, so Intel has their own implementation of one API. This is the Intel one API products and toolkits. So it's the implementation of the specification plus other things like analysis and debug tools to help programming. And you can get access, like early access to this at the link I have there. I talk a little bit more about that later, but they have access to a cloud platform access where you can log in and try running these products, but also you can download it and run it yourself. And so the software on Aurora will contain many of the products and toolkits in one API. A lot of these are familiar things that you've seen before. And so with that, I will move into the tools and libraries. So if you run on Theta at Argonne or other Intel systems, a lot of the software that we have on Aurora is very similar to the software that you've seen before. So for example, vTune and Advisor. So will be supported on Aurora, just like they've been supported on Theta. So vTune is a profiler, like it's a very widely used performance tool. It currently runs on Intel integrated GPUs, and it will be supported for future GPUs. So you can do things like see the kernel time of the code that's running on GPU. You can use it to dump the gen assembly to see what the assembly looks like. You can get memory bandwidth of the code running on the GPU, a lot of useful performance information like that. There's also Intel Advisor, which is nice. You can get do a nice roofline analysis so you can see how close your kernel is to peak bandwidth and peak flops. There's also a offload analysis tool, which you can take your code, run it, and it will give you suggestions on what parts of it would be profitable to offload to GPUs. So you would run your code, it measures performance, and then gives suggestions based off of that. It takes into account things like overhead from data transfer and kernel launch. Basically, this is useful if you have a big application, you don't know where to start. You can run this and at least get some sense of what you should offload to a GPU. Then briefly, Intel MKL will be supported just like it's supported on many other Intel platforms. Intel always does a really good job of optimizing their math library functions for whatever architecture they have. So just like they have optimized versions for KNL, they also will have optimized versions for Intel GPUs. And Intel MKL is part of the one API specification document. So it's one MKL. And then I wanted to mention there's also support for those other two pillars, the data and learning pillars. So there are a variety of libraries that support AI and analytics. So there's Intel's Deep Neural Network Library, 1DNN. This is implementations of high-performance primitives that accelerate deep learning. And this is sort of what powers TensorFlow, PyTorch, Intel Caffe. And you can try this on Gen 9 today. There's also Intel DAL, which is the data analytics library. This contains a lot of optimized machine learning algorithms, and this is what powers scikit-learn. And there's also Apache Spark MLlib, which is the machine learning library for Apache Spark. Okay, so what if you want to try this out now? There are a lot of different ways to, if you want to get started porting for Aurora or just see what the software is like that I've talked about. So one that I mentioned before is what's available from Intel. So they have a cloud platform, Intel's Dev Cloud, and you can apply for access at that link. And then you get the ability to SSH into some computers that have a bunch of, I think, Gen 9s on them, and access to the different toolkit software. and then you can run and play around with and try porting your code with a lot of the software that I talked about before. I've done this. It's very easy to use. You don't have to download anything, so sometimes that's nice. But if you want to download the toolkits yourself, that's also an option, and you can try them on your laptop. Additionally, we have test beds here at Argonne. So Intel's JLC system, which is the Joint Laboratory for System Evaluation. Here we have 20 nodes of Intel Xeons with Gen 9, and no NDA is required to get access to them. There's also a lot of the open source software that I mentioned, like SYCL, OpenCL, a lot of the tools you can use without any NDA. And we do encourage people to apply for accounts, like email me or Sudheer, and try to get, if you want to, you can get accounts and try running on these to start preparing your code. There's also Intel's Aurora SDK, which is similar to some sense to the One API toolkits, but it might diverge in the future or have additional things. So there is an NDA required to try out Intel's Aurora SDK. But if you are part of ECP or ESP project, we can probably get you on the NDA. So again, just let us know. And this has many of the compilers, libraries, and tools that I talked about. And we do want as many people as possible to try this out. We're really excited about Aurora, and we want people to get their code ready. So please don't hesitate and let us know if we can help you get access. And also, if you have workloads that are interesting to you, just please send them to us. We really want to help people get ready for Aurora. So yeah, just let us know. And that's all I had, so I'm happy to take any questions.
Thank you, Colin. We have a couple of questions. So I go back to, will there be support for Intel threading building blocks? At what level? For example, will Intel be optimizing the TBB runtime for Aurora in any way?
So TBB is, I think, part of the One API specification, and I think some of this optimization work is going on, but again, most of the flops are on the GPUs. So I think most of the focus is on optimizing SYCL or DBC++ and OpenMP to run on Intel GPUs.
Okay. Will OpenMP work with Intel USM?
Yes. So we have
And so, I guess the following question was, so no need for map directives other than better tuning?
Yeah, I mean, in general, map directives, if you use an array inside of a target region, you will map implicitly, like the OpenMP will map implicitly for you. So yeah, I think the quick answer to that, the simple answer to that is yes, but yeah. It's always useful to explicitly say what you want.
Yeah. Thank you. So the next question is, can these tools be used on a CPU-only system? For example, could I run a CPU code on my local system and use these tools to figure out what parts should be offloaded to GPU?
Yeah, so the offload advisor part of the part of Intel Advisor, you can run, that only runs on a CPU and suggests what to run on a GPU. But yeah, feel free to let us know if we can either try to get you access to JLC, or you can apply for access to the Dev Cloud, or Intel's Dev Cloud, or Intel's One API toolkit and products.
What support for these APIs will there from Cray compilers and tools?
Yeah, so you will have Cray compilers, LLVM compilers probably, and GCC compilers also. And I think a lot of the Cray programming environments.
So the next question is, when should one opt for DPC++ versus OpenMP5?
Oh, I mean, to some extent, I mean, that has to be up to the programmer. I mean, in both cases, you can run somewhat similar program abstractions, and you can run on the GPU. But with data parallel C++ is really, if you like C++ style programming and like you're comfortable with lambdas and a lot of sort of the C++ type of stuff, then DBC++ is probably a good fit for you. You can still express you can still write C++ code with OpenMP5 in it as well. So it's sort of whichever one looks more intuitive to you.
Yeah, I would say it's a preference for the users. The next question is, what C and Fortran compilers will be supported on Aurora? I think you just mentioned that. Will there any LLVM-based Fortran or C compilers be supported?
Yeah, I think LLVM, C, and Fortran should be on Aurora.
The next question is, so Cray compiler will work DPC++?
So DPC++ should be part of Intel's DPC++, like Intel's compiler only.
Okay. Intel One API's compilers ZPC++ and ICC Next Gen and i4 Next Gen are based on LLVM, ICC Classic, and i4 Classic, also provided by One Offload. Only LLVM-based compilers offload. I think this is just a statement.
This is like the answer to the previous question.
Yeah. Okay, so are there any more questions? Well, if not, I would like to thank Colleen and Sudheer again for this talk. This was our last talk for the year of 2019, and if you have any suggestions or comments, please let us know please let us know, and have a great holiday, everyone. Thank you.
Thanks.
Thank you.
Thank you.